All right, you guys. So today we're going to talk about a couple more things. We're talking about summation notation, integration by parts. Now, summation notation is tricky. It's one of these things that's like, how do I, like once you get the hang of it, you can recognize it. So it's a little bit tricky to understand. I also don't want to spend too much time on it because, I don't know, I think like last year on the AP test there was maybe one question about this. And so it's like, how much time do we want to spend, right? But anyways, okay, so take a look. If we've got this definition, we've got this integral right here, right? The integral from a to b of f of x. And we got all this crazy stuff, and it's like, dude, what the heck? Okay, so let me kind of give you a visual. I was going to draw this out, but I found a pretty decent visual that I want to show you. All right, so kind of like muted this guy, but we can look at his drawings. Okay, so this is like, okay, two rectangles, right? And he's got these little calculations over here. He's doing right-hand rectangles. The actual integral is 21.333, okay? Two rectangles, all right, we're at 40, okay? And then we're dividing it up into three rectangles, four rectangles, 5, 6, whatever. And the number of rectangles as it's increasing up here, and we're getting closer and closer and closer, all right? So can you guys picture this? Like I'm just making so many rectangles. So how do I get this exact integral under the curve? How would I get the exact thing? Well, eventually I would want to have an infinite number of rectangles. Does that make sense? And the width of each of these rectangles is still getting like smaller and smaller and smaller. So when we have like 26 rectangles, you skip past a little bit more here to see what else we're doing. If we've got, you know, and it just like keeps on, he's just like kind of talking through here, I think. Okay, making more and more rectangles. All right? Okay, so if we take a look at this, what this is saying is, okay, n is the number of rectangles. And so what's happening here is my rectangles are going to infinity. I'm getting like an infinite number of rectangles. Okay, starting from, and I'm summing them all up from 1, the first, rectangle, I'm summing them all the way up until infinity. Okay, this is a summation symbol, this thing right here. It's a sigma letter, it's capital epsilon, I believe, and it tells us the summation of all these things, okay? Now, think about what a rectangle is. A rectangle that we talked about in the last section is basically the base times the height. So, you know, we have this, like, curve or whatever, and I have this rectangle, okay? The base is what they're calling here delta x. This is the base of my rectangle, all right? And then in here, we're going to do a right-hand rule just because we've got to pick one or the other. And it'll be, I think, you know, easy to just stick with a right-hand rule, and then we can modify it for left-hand. So we're doing a right-hand rule. So what's the height of this little rectangle I drew over here if this is like delta x, and if I started at, 1 or whatever? Well, it's f of whatever this point is right there. All right? Now, the point that we're starting at is, if you look over here, where are we starting at? A. We're starting at A. So it's the height of A, but since it's a right-hand height, it's like a little bit more over, and we do that like k times. So if it's the fourth rectangle, we started at A, and we added 4 like widths of rectangles. If it's the 10th, we started at 10 and added 10 widths of rectangles. And so basically that's the height. You know how we did base times height is f of x or whatever, okay? And then here's how this works, all right? You got to find the width. This is one of the more important things, and this is usually, if you can figure this out, you got it set, right? So the way I figure out the width, we talked about this last time, is we go b minus a, because that's the length of the entire thing, divided by number of rectangles. If I can get b minus a divided by the number of rectangles, and then I start at a, whatever this first number happens to be, and I add k times the width a bunch of times to do a right-hand rule, okay? So let's just see if we can set this up. You guys, you never really have to work with it. It just has you like go back and forth from one to the other. All right, so check it out. First of all, I'm going to go ahead and find my width right here. So my width is, if I'm going from 1 to 4, so I'm going 4 minus 1 divided by the number of rectangles. and the number of rectangles is going to infinity, right? Okay, so I'm kind of patterning from right here. All right. I mean, the hardest thing I guess would be to like memorize that, but let's just see if we can kind of understand it. I'm trying to go to an infinite number of, sorry, we don't write infinities in summations. I'm trying to go, the limit as n goes to infinity, up to n, and then we just start it with k plus 1. So like the first rectangle, second rectangle, third rectangle we go through. Okay? All right, now, the base is right here. The base of each rectangle is 3 over n. So I'll go and put that right there. And then this inside here is f of, right? And then it's whatever I started at, which is 1 plus the width of the base k times. Well, they put the k in front of it, but that's fine. So it's f of 1 and then k rectangles with the width of 3 over n. Now, if it's f of that, you guys, I need to just plug it into x to the fifth. So it's 1 plus 3 over n k to the fifth. Okay, because I'm like plugging it in right there. And that's it. That's my answer. All right, this whole thing right here is nice. Okay. So, kind of confusing. Let's see if we can work this backwards, right? Let's see if we can work this backwards. Okay. First of all, this is my rule. So, something minus something over n gave me pi over n. So the b and the a, when I fill this in, when I subtracted them, it gave me pi. All right, and you'll see the width like repeated right there. Well, what's a? Well, a you can actually find right here because this tells me what rectangle, like where to start. So if a is pi over 2, and the interval that I'm looking at went by pi, okay, this is pi over 2, and this is 3 pi over 2, because then the width of that is pi. Okay, makes sense? So by looking at that, that helps me. So that tells me a. This right here tells me the distance between a and b, and then this right here tells me what I'm taking the integral of. And I'm taking the integral of sine x dx. And I think that's all it was. Yes, that's it. Okay? And there you go. That's basically all that you're doing. We're just looking at right Riemann sums. You could do the left, except for it says it would go k equals 0 to n minus 1. But it's really just kind of like recognizing and writing this back and forth. Okay? Don't get too high up on it. We'll try to do some questions about it. Not a huge deal. All right, integration by parts. Now, this is where we're going to focus like most of our lesson on, okay? And I want you guys to remember one thing. I want you to remember integration by parts is, do you remember I told you guys there's no product rule for integration? Like, and there's really not, but this is what we do when we want to do a product rule. So the product rule of something like x with e to the x, or e to the x sine x. It says with transcendental functions, e to the x, or trig functions, or stuff like that. It's like an integral for product rules. We call it integration by parts. Okay. All right. So the first thing is, where the heck does this formula come from? Let me go ahead and show this to you. Okay. The derivative of uv. So this is a product rule, right? So the derivative of uv is going to be. And by the way, we're taking the derivative with respect to x, which is also implicit. All right. Is going to be derivative of the first, which is du dx, times the second, plus the first, I'm using my v's are looking too similar. What do I do? Du dx times the second. There we go. And then the first times derivative of the second. Okay? Just simple, like product rule right there. All right? And so now we can take the integral of each part. Take the integral of that with a dx, the integral of that with a dx, and the integral of that with a dx. Okay? Look what I have. Now, right here, you guys, Second fundamental theorem of calculus, if I take the derivative of an integral, I just get uv. You guys see that? Take a derivative of an integral. Okay? Right here, see those dx's cross off? This is going to be the integral of v du. Alright? And then this, see how the dx's cross off, is going to be the integral of u dv. So I kind of got rid of all my x's, any like dx or whatever. I got rid of that, and I got this formula. Okay? Now, it doesn't really help me. This like tells me u times v, but I'm trying to find some integrals. Now, what I'm going to do at this point is I'm going to solve for u dv, right, by subtracting this to the other side. So uv equals the integral of v du. Sorry. Let me write this again. Jeez. Okay. uv minus the integral of v du equals the integral of u dv. Okay? This is integration by parts. You can look at it either this way with the primes and stuff, but I particularly like it like this. So I'm going to use this one right here. Alright? So what you do is you, on your original function, one of the things is a u, one of the things is a dv. Alright? And then you have to memorize it. Now, memorizing this sucks, right? It's a little bit tricky, so let me teach you how we're going to memorize this. I want you guys to remember this. Ultraviolet voodoo. Alright, there's a special kind of magic that we practice here in calculus class. We practice ultraviolet voodoo. Alright? Now you guys cannot tell anybody about ultraviolet voodoo. You understand? This is a secret only for calculus class. Check this out. When you do integration by parts, we do ultraviolet voodoo. Okay? Ultraviolet voodoo. That's all we're going to remember. Alright? So here's your strategy, okay? First, you have to pick out of the integral a u and a dv, okay? U needs to be the part where the derivative gets simpler, or at least no more complicated. So, u, like derivative of sine is cosine, that's fine, it gets simpler, it doesn't get too much more complicated or whatever. Okay, dv needs to be the more complicated part. Alright, the part that can be easily integrated. You typically have two choices. Alright, so look here, you guys. So in this question, am I going to let u be x and dv be e to the x? Or am I going to let u be e to the x and dv be x? Okay? You really only have two choices. If you try one and it doesn't work, go try the other one. Alright? Let me show you what doesn't work, what I mean by that, okay? So let's look at this one, and let me do it wrong first. Like, I don't know, it's not cool, but let me do it wrong first, alright? So u, let me go ahead and pick that as e to the x, and dv as x. Okay, this is wrong. Okay, so don't write this yet, just watch what happens. Alright, so the integral of u and then dv, which would be x dx. And then it's ultraviolet voodoo. Okay, ultraviolet voodoo. So let's come up here, let's fill out my box. The derivative of e to the x is e to the x. This one's going backwards. The integral of x is x squared over 2. This is not looking fun, guys, right? Because then I have to integrate x squared over, well, okay, let's just do this whole thing. I'd go e to the x, u, v, x squared over 2. And then I have to integrate x squared over 2, and then e to the x dx. And, like, it's not going to work. It gets too complicated, okay? So when it gets too complicated, you're like, oh, crap, I did that wrong. So let me go back and do this again. All right. This time we're going to pick it the right way, okay? And the right way for this one is u is x, and dv is e to the x dx. So you guys see how, so here I put here, right? And here I put here. Okay, you gotta fill both of those in. Alright, so u and dv. So, now this is the right way to do this. Okay? What is the derivative of u with respect to x? Okay, so that's du, that's 1 dx. You guys know how to do that. And then what's the integral, because now I'm going backwards, of e to the x. Well, see, we like this because the integral of e to the x is e to the x. And when we integrate, a dv and a dx go away. Okay? So I've got all my different parts, so if you can see all those different parts. So, here's how this works. This is u dv, okay? And I'm going to write my formula first because it's ultraviolet voodoo. Is it minus the voodoo? Yeah, minus the voodoo. You got to remember that. Okay, ultraviolet voodoo. All right. And, okay. This is this part. Alright? And so it's ultraviolet voodoo. Okay, so UV would be x e to the x. And then it's the integral of v du. Okay, here's a v. And here's du. And then it's like, sweet, I can integrate that. So it's x e to the x minus the integral of e to the x is e to the x plus c. And that's integration by parts. So I was able to integrate something that I couldn't integrate before. Alright? You guys want to see kind of why this works? This part's pretty cool. You do not have to write this down if you don't want, but here's why this works. Alright? Let's see here. Yeah. Okay, perfect. Alright. Let's now, just to check it, let's just take the derivative of this, okay? And if I was doing a derivative of this, guys, I'd have to do a product rule. Derivative of the first times the second, plus first derivative of the second. And then over here, the derivative of e to the x is e to the x, and the derivative of a constant is 0. Well, notice what happens. E to the x minus e to the x cancel out, and I'm just left with x e to the x. So it simplifies back up to what my original problem was. Alright, we're not going to check every time, but that's kind of cool. Okay? Alright, let's do some more integration by parts. So when you write it down, we're going to go u. We're going to pick the u and the dv. So I'm going to say, let u equal, and let dv equal. Alright? It's not always going to go in order. So let's just see. Again, if I pick x for my dv and I get x squared over 2, it's like, no. That's not good. So I'm going to pick u is x, and dv is sine 3x dx, okay? Alright? And then I gotta figure out my next part, okay, which is du and then regular v. Alright, well, du is the derivative of that. Derivative of x is 1 dx. And then the integral of this, so I gotta integrate this one now to go backwards. Guys, the integral of sine is negative cosine. And remember, this is like u sub, but not really. It's that shortcut. It's reverse chain rule. And if it says 3x, instead of multiplying by 3, we divide by 3. Okay? So I finished on my box. And then I've got right here, this is the integral of u dv equals the integral of, or no, not integral, if we start with ultraviolet. Ultraviolet voodoo. Ultraviolet voodoo. Okay? Let's go start writing all this stuff in. So this equals u times v minus the integral of v du. Okay? I'm gonna move this over to give myself some more room. Whoops, these. Okay, there we go. All right, you guys, so this first part's fine. It's just negative 1/3 x cosine 3x. Okay, this one right here, negative, negative, I'll go ahead and make that a positive. The integral of cosine is sine, and it's another reverse u sub because I have times 3x, so it's 1/3. So I'm just going to change that to 1/9, basically. Let's see, okay? All right, so I get negative 1/3 x cosine 3x and then 1/9 of that. Perfect. Perfect, perfect. All right. Now, integration by parts is how we integrate things like arc sine, because I don't know what the integral of arc sine is. We don't know it, but we can use integration by parts. Now, the only thing I know about arc sine is that the derivative of arc sine is 1 over square root 1 minus x squared. I remember that. Right? I remember that that's the derivative of arc sine. So if I'm trying to say that u equals something and dv equals something, u has to be the arc sine, because I know what the derivative of it is. It just like has to be. U has to be arc sine x, and dv has to be dx. Okay? Now, let's finish this out. du is 1 over the square root of 1 minus x squared, dv, because that's the derivative, or sorry, dx, and then dv is dx, so v, if I go backwards, what's the integral of 1? It's just x. Okay? So there's my chart. So now I go like this. Alright. Color that'll stand out. So this is u, this is dv, so it's going to equal ultraviolet voodoo. Okay? Ultra, so it's arc sine violet x minus the integral of v x, and then du, you guys, du is all this stuff. So du is 1 over square root of 1 minus x squared dx. Okay? Now look, this part of the problem is done. That's what we like. And now we just have to focus on this part. And guess what this part is? This part is a u sub problem. See that? Because, okay, so I'm only focusing on this second part for a minute. If u is 1 minus x squared, du is negative 2x dx, negative 2, negative 1/2, so I just made that positive, right? So this turns into 1/2 1 over root u du. Okay. Yep, that's good. Which is 1/2. When I bring that up, it's u to the negative 1/2. So if I add 1, it's u to the 1/2 times 2 over 1. Okay, so it's just u to the 1/2. And u was 1 minus x squared. So this equaled, the first part of it was arc sine x times x. We good if I just put that other times x up here because it'll look better. Arc sine x times x. The minus changed to a plus, and then I integrated that, and then that whole entire thing is my answer. Okay? Integration of parts, kind of cool, guys. I don't know, I kind of dig it. You know? I kind of dig it. Alright, let's do a couple more. Alright. Is this integration by parts? Yes, it is. You guys notice, if it was this other way around, if it was that, cool. It's u sub. Right? If it was the other way around. But it's not. And this is an integration by parts. Okay? And so I'm going to go, okay, let u equals something and dv equals something. We want this to get simpler. We do not want that to get big, x to the third over 3. So I'm going to let u be 2x, and I'm going to let this be sine of 2x dx. And then we're going to go find our du. The derivative of x squared is 2x dx. And then I'm going to integrate this to go backwards to v. And the integral of sine is negative cosine, and I have to put a 1/2 because of reverse chain rule. Okay, instead of multiplying by 2 and dividing by 2. Whew. All right, here we go. So the integral of u dv equals, gosh, let me, yeah, I have room. Ultraviolet voodoo. Okay, so it's ultraviolet UV, and then it's integral of V negative 1/2 cosine 2x times 2x. Alright. So, okay, so this is cool. So we've got this, and this part of the problem is done, you guys, right? So this part of the problem, I'm going to put the 1/2 out front. And then minus a negative, I'll go ahead and put plus. And then can you guys see that right here, the 1/2 and that 2 cancel out? So it's plus x cosine 2x dx. Now, the whole point is that now we have to figure out how to do that part. And guess what this is? Another ultraviolet voodoo, another integration by parts, right? So we've got that part, and now we have to go, let u equal dv equal, u is x, dv is cosine 2x, which means as I go backwards, or this one I go forwards, du is 1 dx, and v is integral of cosine is sine 2x 1/2. Okay? And so when I do ultraviolet voodoo on this one, ultraviolet, that's UV, minus the integral of v du, which is just dx. And now it'll work. Oh, and don't forget, I still have this. Okay, so my final answer is negative 1/2 x squared cosine 2x plus 1/2 x sine 2x minus, okay, I've got 1/2. The integral of sine is negative cosine, so that'll be plus cosine, another 1/2 plus the last one can go like a fourth. There you go, all right? Now, can I tell you guys something? Super fun, right? Super cool problem. Not on the AP test. I mean, very, very, very unlikely that a double integration by parts should be on the AP test, okay? We just look at it because it's cool and it's fun and I'll shoot, like, see when that's going to happen. But a double integration by parts, you guys see how long that took me? If that showed up on a multiple choice, I wouldn't even waste my time. It's not worth the points that you would get back. You know what I mean? So, anyway, that's that. All right, last one. Now, this is a definite integral. X squared to get simpler. So, that's going to be u right here. And then that's going to be dv. Okay? So, let u is x squared. And dv equals ln x dx. Then, du is 2x, and v is integral of ln. Oh, wait a minute. I can't take the integral of ln. I can take the derivative of it, but we don't actually have an integral of ln. So, it was following this pattern where the x was always like the u, it was, but like it's not now. It doesn't actually work that way. So it's like, oh gosh dang, okay, so if this isn't going to work, then let's try something else, where this is u, and this is dv, okay? So now u is ln of x, and dv is x squared dx, and let's see if that works, because it wasn't going to work before. Alright, du is 1 over x dx, v is x the third over 3. Okay? Well, it's like kind of like, but let's see what happens. So u dv, this is going to equal ultraviolet voodoo. Alright, are you guys enjoying saying that over and over again? Because I am. Okay. Ultra, ln of x, v minus the integral of v du. Okay? This first part is done. Now I have to just work on the second part. So that's an integral, but you guys, x to the third and x can cancel out and give me x squared. I can leave the 1/3 right there. It's like 1/3 x squared. So the integral of x squared is x to the third over 3. So now I have ln of x to the third over 3, minus 1/3 x to the third over 3, plus a constant, except for I'm actually not doing plus a constant on this one because now it's having me evaluate it from e to 1. So evaluated from, and then we do top minus bottom. So I want you to remember a couple of things here. Okay, so guys, remember that there's a couple of things I told you. Let's just review really quickly right over here. The ln of e is 1, the ln of 1 is 0. Just remember that. So, okay, top minus bottom. Okay, when I put e in over here, the ln of e is 1. So it's 1 e to the third over 3. When I put it here, that's basically going to be 1/9 e to the third over 9. So it's going to be e to the third over 3 and another 1/3, so it's e to the third over 9. Okay, then when I put in a 1, ln of 1 is 0, so I don't even need to do that. Minus 1/9. That's pretty much my answer. I mean, if you want, let's see, we could put it all over 9, I guess. That would be 3 e to the third over 9 minus e to the third over 9 minus negative would be plus 1 over 9. So, final answer, I'm going to go with 2 e to the third plus 1 over 9. If it was like multiple choice or something. And then, let's see, if I did this right, I'll be very happy. 2 e to the third plus 1 over 9. Let's go ahead and put this in x squared ln x into our calculator. Okay, because every time I have endpoints, I just like to check out my calculator and make sure I'm keeping up with my calculator skills and to make sure I did it right. Okay. Alright, so here we go. We've got, come on, okay. Okay, so if I do the integral from 1 to e, I use that little e right there, of x squared ln x dx, okay? Is that the same as fraction 2 e to the third plus 1 over 9? Let's go! Alright, how do we feel about that, guys? How do we feel about integration by parts? So, when I was saying not on the AP test, y'all, I meant number 6. Not number 7. Number 7 is dubs, right? Okay, so yeah, I was saying like, number 6 maybe. So cool. Double integration, probably we're not going to see that on the AP test, right? But number 7, sure. No worries about that one. Okay. Wowzers, guys, that was a lot. I hope that made sense to you. Excited to do some integration by parts with you in a little bit.